Okay, we will go through the example of problems in class 11, physics, chapter 6, work, energy and power. Okay, see, I will show you some equations. This is one of the kinematic equation. V square minus U square equal to 2as, where U is the initial velocity, V final velocity, A acceleration, S distance. Okay, the work done is the difference in kinetic energy. Okay, of m V square minus U square, that is final kinetic energy minus initial kinetic energy. This is the difference. Work done is Ft cos theta, force into displacement cos theta. Cos theta, cos angle can vary from +1 to -1. Okay, cos 0 is 1, cos 180 is -1. Okay, similar. So the work can be, this product can be positive or negative. Okay, but kinetic energy, you see, because you square it, always positive. Okay, mass is positive. Okay, when you place something at a height, say h, the potential energy is increases depending on the area, is directly proportional to the height. But when you drop it, then the potential energy decreases and the kinetic energy increases. The kinetic energy will be maximum here. So the potential energy will be maximum at the top here. A potential energy at A is mgh. Okay, mass into gravity into height. Okay, but if you put it down, potential at the ground at C, then it will be ulta, that is potential energy will be 0, the kinetic energy will be of mv square. Okay, at this ground we are converting that potential energy into kinetic energy. Okay, then from that equation m cancel out, v square equal to 2gh, then velocity equal to square root of 2gh. Okay, this is the cosine function at 0, 90, 180. 0 it is 1, 180 minus 1. Okay, now in this chapter there is a conservative forces. Potential energy, kinetic energy, they are conservative. Non-conservative energy like friction, magnetic force, electrostatic force, air resistance, these are all non-conservative. Elastic collision. Okay, here in this collision kinetic energy is conserved, linear momentum also conserved. Okay, so when body of mass m1 collides with m2, this is the relation, conservatively m1 v1 initial equal to m1 v1 final plus m2 v2 final. That is this is the momentum conservation. In the inelastic collision, the momentum is still conserved, but kinetic energy is lost. Okay, it may be released like a sound due to collision. After the collision, these two masses will unite, like they will be combined. Okay, this is when they are joined, this is called inelastic collision. Okay, so here kinetic energy is lost, so the initial kinetic energy will be greater than this final kinetic energy. Okay, okay, question: an electron and proton are moving under the influence of the mutual forces. In calculating the change in kinetic energy of the system during the motion, one ignore the magnetic force of one another. This is because see, the magnetic force is always perpendicular to the velocity. Okay, to the movement. So here you see these velocity, magnetic field and magnetic force all are perpendicular. Okay, VBF. Okay, so when they are perpendicular, then that the work done is FD cos theta. Okay, that is cos 90 is 0, so that is magnetic force is 0. Work done by the magnetic force is 0. Okay, this is magnetic force, it's not a magnetic field. So magnetic force is perpendicular to the displacement. Work done equal to FD cos theta, because angle is 90, so cos 90 is 0, that is work done is 0 here. Okay. Work done FD cos theta, force displacement angle, okay, because 90, so this is 0. So that means the magnetic force do no work on the particle. Okay. A proton is kept at the rest. A positively charged particle is released from the at a distance d in the field. Consider two experiments. One in which charged particle is also a one is the other particle is also a proton. In another is positron. Okay. Proton and positron they have same charges, but proton is mass is much higher than the positron. In the same time, okay, the work done on the two moving charged particles. Okay, positron have the same charge, the force will be same, because the force is dependent on the charge. The proton positron have the same charge, force will be same. Only the mass this is okay. Work done is force into displacement. Okay, force is same, but the displacement will be more for positron, because it is the weight of the proton is much higher than the positron, so the work done will be more for positron, because of this d is more. Okay, change in momentum is same, so the velocity is more for the positron. So more in case of positron work done, because of the more displacement, as the positron moves away over a larger distance. Okay, a man squatting on the ground gets up from stand. The force of the reaction of the ground on the man during the process. Okay, initially it will be more due to friction, but when he stands up, the normal force will be opposite to that of the gravitational force. Okay, initially it will be more. Okay, due to the friction, initially you will have frictional force as well as gravity, but when he stands up, then the only force is the gravity, that is equal to the normal when standing. Okay, at burst, okay, the force of reaction at first is greater than mg, then later becomes equal to mg. Okay, okay, a bicyclist comes to skidding and stop at the 10 meter. During the process, force on the bicycle due to the road. Okay, this is directly opposed to the motion. The work done by the, see here they are asking work done by the cycle on the road, they are asking. Okay, work done, so road is not moving, so the work done, there is no displacement of the road, so work done is FD cos theta, because d is 0, the work done is 0 here. Okay, road undergoes no displacement. So here you see work done by the cycle on the road is 0. Okay, because road undergoes no displacement. A body is falling freely under the action of the gravity in the vacuum. Which of the following quantities remain? As I told you, when it is falling, its kinetic energy increases, but the potential energy decreases. Potential energy depends on the height. Okay, so the mechanical energy is conserved. Total mechanical energy is conserved, assuming the no friction in the air, no resistance in the air. Which of the following quantities remain constant? Okay, This is mechanical energy is conserved. You see at this side, this is the potential energy. At middle, potential energy plus kinetic energy. At the lowest, only kinetic energy. But the energy is constant. This energy at all the levels. Okay, here. So the total mechanical energy of the system is system is conserved if the forces doing was are conservative. Okay, so here mechanical energy, sorry, potential energy, kinetic energy is the doing work, so it is conserved. During the inelastic collision, okay, inelastic between the two bodies, which of the following bodies remain conserved? So inelastic momentum is conserved, but not the kinetic energy. Kinetic energy will be lost. Okay, in inelastic, the momentum is conserved here. Two inclined frictionless, okay, there are no friction in this inclined surface tracks. Okay, one gradual and other is slip. Okay, this is gradual and this is slip. From two stones are allowed to slide down from the rest, one on each track as shown. Okay, one on this track and one other on the first stone, second stone. Okay, now the height is same. Okay, that means the velocity will be same, both will be rolling because of the 2gh, v equal to 2gh. Okay, but here the track is lengthy, so this will take some, the here it the acceleration will be more, it will reach fast here, so here acceleration will be less. Both stones reach at the position with the same speed, but the stone 2 reaches the bottom earlier than the stone 1. H is same, so V is same for, because 2gh, H is same, so V will be same for both the stones. But here theta, this is more than this theta, then the acceleration will be more, because this acceleration is mg sine theta is the force. So the sine theta, theta is more here, so the acceleration will be more here, the acceleration will be less here, so this will reach earlier than this. Okay, acceleration equal g sine theta, g is constant, the theta is more here, so this value will be more, so acceleration will be more this side, so the ball 2 will reach earlier than the stone 1. The potential energy function for a particle executing a linear simple organic motion is given. Okay, this is the potential energy equal to of k into x. X is the displacement where k is the force constant of the oscillator. K equal to the graph V of x versus x is on the particle total energy. Okay, kinetic energy plus potential energy tends back when reaches, this is the maximum height where it will reach. Here k indicate the potential energy, V is the potential energy, k is the kinetic energy respectively. So they are asking at x equal to plus x. Okay, at x equal to this point, which of the following is correct? at x equal to this thing, here kinetic energy will be 0, potential energy will be the total energy. So the potential energy is totally, kinetic energy will be 0. Okay, here at this, here kinetic energy will be maximum, potential energy will be 0. Okay, they are asking it at this. Okay, at this point. So that point potential energy will be the energy, and kinetic energy will be 0. Two identical ball earrings are in contact with each other and resting on this table are hit by the another ball bearing the same mass. Okay, the same mass, both this and this are same mass, moving initially with the speed we have shown here. The collision is the elastic collision, so that means momentum and energy is conserved. Okay, which is conserved. Which of the following is the possible result after the collision? After the collision, so here is elastic collision, momentum and energy is conserved. Okay. Okay, in the first case, after the collision it is of mv square. In the second case, this one, okay, because they are given the mass. This is the case 1. This is the case 1. E by 2. Okay, this is the case 1. Okay, this is the total kinetic energy. Okay, sorry, this is the case 1. Okay, so half into mass into velocity v by 2. Okay, 2 cancel out. This is 1 by 4 mv square for the case 1. For case 2, so we have v. Okay, and case 3 we have v by 3. So v, this is mv square, this for the case 3. So the kinetic energy is conserved only at the here in the second case. Okay, for the scenario 2, the elastic collision, both momentum and the kinetic energy is conserved. Okay, in this case there's 2 only is conserving the, so this is the correct one. Okay, in this case, body of mass travels in a straight line with velocity. Velocity, this is the function of distance and acceleration. The work done by the net force during the displacement is 0 to 2 meter. Okay, 0 to 2 meter. Okay, this is the given thing. Then this is the velocity. The acceleration is given. Work done from x equal to 0 to at x equal to 0, and the velocity will be 0. At x equal to 2 meter, this is the velocity a into, okay, after substitution you will get. So work done is change in kinetic energy of mv square, final velocity minus initial velocity. So we get this answer. This answer. A body is moving unidirectionally under the influence of the source of the constant power supplying energy. Which of the diagram is shown here shows the displacement versus time. Okay, so here we have to use some kind of dimension analysis. Okay, power is equal to force into this is the displacement by time, because it's constant power. So the force into velocity is constant. Force mass into acceleration, m into acceleration lt minus 2, velocity lt minus 1, constant. If you use that dimension analysis, you will get this. Okay, so this is that curve. Which of the diagrams shown in here most closely the variation of the kinetic energy of the earth that moves around the sun? Okay, earth. So the speed is maximum when earth is closer to the sun. The kinetic energy will be more that time, and the minimum when it is away from the center. Kinetic energy, so kinetic energy varies, but kinetic energy is always positive, okay, because of the square, velocity square. So this will be the thing, not this. Which of the following diagrams shown below represent the variation of the total mechanical energy of a pendulum oscillating in the air? Okay, the mechanical energy of the pendulum go on decreasing because of the air resistance. So it will go on decreasing like this only. It will not oscillate. So it will. A mass of IAG is moving in the circular path of radius 1 meter. If the mass moves, okay, 300, okay, the kinetic energy would be 14. So this is the given mass 10 kg, velocity, height, gravity, initial potential energy mgh. Okay, this one. Kinetic energy is half mv square. Okay, this one. Initially P plus the total mechanical energy is this one. Okay, final B potential energy will be 0. Okay, so the kinetic energy will be the mechanical energy because of conservation of energy. Okay, final potential energy will be 0. Sorry, linear, no, not this. This one, okay, 5 kg, the radius, this is the per minute, the 300 revolutions per minute, so this many revolutions per second. Okay, the angular velocity is equal to 2 pi into pi, that is 10 pi radians per second. The linear velocity equal to angular velocity into radius. Okay, angular velocity is radius, kinetic energy is equal to half m v square linear velocity. So this one. 14. A raindrop falling from the height h above the ground, okay, attains the near terminal velocity when it is fallen through the height of 3/4. Up to 3/4, it reaches the terminal velocity. Which of the diagram shown correctly shows the change in kinetic energy and potential energy? See, kinetic energy increases, potential energy decreases. Okay, potential energy decreases, kinetic energy increases till it reaches the terminal velocity. Okay, this is the terminal velocity. Okay, this terminal velocity is due to the air resistance. Okay, at terminal velocity kinetic energy will be constant, so when reaches the terminal velocity kinetic energy will be constant here. So this is the curve. 16. Okay, start part event as one athlete throws start part, okay, 10 kg. Here okay, this is what I have shown here. This angle does not matter. Initial that mechanical energy is conserved here. So 16. Okay, this one. Okay, the initial mechanical energy is the potential energy, kinetic energy, and final because potential energy will be zero out in the ground. Okay, so the kinetic energy is the total energy. Which of the following diagrams correctly shows the change in kinetic energy of the ionosphere? Okay, the kinetic energy will be increases till it reaches the terminal velocity. Okay, kinetic energy will be weakened till it reaches this terminal velocity. Then after that it will be constant. Okay, a cricket ball of the mass moving with this speed hit the bat. Okay, middle of the bat held from the by the batsman. Ball moves straight back to the bowler, so the it will move back with the same velocity but the negative after hitting the bat. Assuming that collision between the ball and is completely elastic and it remained in contact. Okay, this many seconds it will be inelastic it because of touch. So but generally collision is elastic. The force that the batsman has to apply to hold the ball firmly in place would be, okay, 18. Okay, this is the mass velocity. This is in meters per second, 35 meters per second. The change in momentum divided by time. Okay, change in momentum will be final momentum because of the negative velocity will be negative when it hits back. Velocity will be negative. Okay, so minus me is the final momentum, initial momentum minus initial momentum, that is me minus 2 me divided by the time change in. So after that this is this much force. A man of mass m standing at the bottom of the staircase of height L. Okay, climbs it and stayed at the top. Reaction force is zero because the point of application of the force is not moving. The friction is zero. Gravitational force is mgl, and the person's muscular force is opposing this gravitational force. Work done by the all forces on the man equal to the rise in potential energy. No, that is not correct. Work done is against the gravity. Work done in all forces on the man is zero. Okay, the reaction force from the step does not do any work because the point of application of the force does not move. Okay, here steps is not moving, so it doesn't do any work. Does the no work. A bullet of mass m is fired at this angle and it leaves the barrel. Okay, the bullet has soft target at okay, so you can go through this detail here. This is the answer. Two blocks of mass m1 and having the equal mass. Okay, they are having equal mass, free to move on the horizontal frictionless surface. Frictionless surface, same mass. M2 is attached to the massless spring as shown in here. Okay, it is attached to the massless spring. So M2 is rest, M1 is moving forward, M2 with the speed. Okay, collides. So while spring is fully compressed, all Ke of M1, no, all Ke, only some part of Ke will be transferred. So here momentum and K, because elastic collision, momentum and K is conserved. Equal mass, when the elastic collision, equal mass they are colliding, then there is a velocity exchange. Okay, velocity exchange. Spring is massless. The final state of M1 is state of rest because of the velocity exchange. Okay, the surface on which blocks are moving is friction, then collision. Okay, yeah, there may be, because of friction there may be energy loss, so it may not be elastic. When there is a friction, momentum will not be when the energy will not be conserved. Okay, very short answer. A rough inclined plane is placed on the cart or maybe, okay, horizontally a block of mass m rests on, okay, 22. Okay, this is the diagram. So here the force, say mg sin theta, work done is force into distance cos theta. Okay, because of the distance it is not moving, so the displacement or distance is zero, so work done will be zero. Okay, no dissipation of energy because no work done. Because that mass m rest, okay, it's not moving. Why electrical power is at all? When the elevator is descending, why should there be a limit on the number of passengers on this? Okay, 23, because to avoid the sudden brake. 23. To prevent the elevator from falling freely under the gravity, so we need power for the elevator. The body is being raised to the height h from the surface of there. What is the sign of the work done? Okay, when it is raised up, the direction of the gravitational force is completely opposite, that is 180-degree difference. 24. See, when it is being raised up, the applied force and this direction is zero here, but in terms of gravity it is 180. Okay, so the work done will be positive. Applied force, the work done will be positive, but the gravitational force it will be negative, because the cos 180 here, theta is between this and this is 180-degree, so it is negative 1, minus 1. Okay, so it will be negative, work done will be negative for the gravitational force. Gravitation for negative, applied for positive. Calculate the work done by the car against the gravity in moving along the straight horizontal, moving horizontally, the mass of the car. Okay, because the angle is moving horizontally, the gravity and the movement displacement, the angle is 90-degree, cos 90 is 0, so the work done is 0 here. 90-degree, it is so gravitational. Work done against the gravity movement is 0 here. Okay, a body falls towards the earth in the air. What is the total mechanism will be conserved? Okay, it will be conserved if there is no air resistance. Resistive force in the earth is non-conservative. 26. Because the resistive force of the earth is also action on the body, which is non-conservative force. Okay. A body is moved along the closed loop, his work done is moving and the body is necessarily 0. If not, state the condition. Okay, 27. Work done over any closed loop is necessarily 0 only if all forces acting on the system are conservative. Okay. In an elastic collision, elastic means both momentum and energy are conserved. Which of the following quantities remain conserved during the short time of the collision of the poles. Atom and collision of the pole both are in contact, so that is it will be inelastic. That time only the fraction, so only momentum will be conserved, okay, during that short time. Inelastic when they are in contact for the short time, okay. Okay, when poles are in contact, they are in the deformation, which means the elastic potential energy which came from part of the momentum is also conserved, okay. Calculate the power of the crane in watts which lifts the mass at the height, okay. 29 power, this is work done by time, okay. The average work done by the human heart, which beats once in 0.5 once is 0.5 joules, okay. Calculate the power is by the hour 72 times in a minute. Okay, this is per beat 0.5 joules. 72 means 0.2 into 0.5. They are given per minute. So divided by 60, you will get this much. Use the example of situation in which applied force does not result in a change in kinetic energy. Okay, charge moving in a magnetic field. So the velocity of a charge won't be affected by the magnetic force. A charged particle moving in a uniform magnetic field, because that magnetic force does no work on the particle, so kinetic energy won't change. Two bodies, unequal masses are moving in the same direction. With here they are moving in the equal, kinetic energy will be equal, okay. Half mv square is equal for the both the bodies. The two bodies are brought to rest by applying retarding force, same magnitude. How will the distance move them before coming to the rest? Because both are having same kinetic energy, the force is changing, kinetic energy is the force, okay. We have to apply the same. 32 work done is change in kinetic energy. Both bodies have the same kinetic energy and hence same amount of work is needed to stop them, okay. Since force applied is same, they will come to the rest within the same distance. A bob of mass is serpentine light string L included the vertical circle as shown below. What will be the trajectory of the when it is cut at B, C and X, okay. Straight line, parabolic, and these three paths. The graph of the potential energy versus distance is shown here. A particle of energy E is executing a motion in it. Draw the graph of the velocity and kinetic energy, okay. This is the potential energy versus the displacement. We need to draw the velocity versus the distance and the kinetic energy versus x. For the complete AF again A, okay. AF, complete AF they are asking. 34. Okay, this one is the kinetic energy, this is velocity. One circle AFA. A ball of mass M moving with the same speed, moving with a speed to not colloid inelastically, okay, inelastically with an identical polar rush, so that For head-on collision, both balls move forward. Okay, the inelastic collision, its still momentum is conserved. Okay, for general collision, the angle between the kinetic energy after collision will be less than the kinetic energy, because kinetic energy will be lost for the inelastic collision. For head-on collision, conservation of momentum. Okay, the momentum is conserved, not the kinetic energy. So based on that, okay, this is the one. Okay, so now they are finding the angle. Consider the one-dimensional motion of a particle with the total energy E. There are four regions here with the relation between the potential energy, the kinetic energy, and the total energy. Okay. See here, when potential energy is greater than the total energy, that means kinetic energy will be negative, and that is not possible. Okay, that is not possible. Kinetic energy can't be negative, so the particle won't be found here. We found here 36. Region A, particle can't be found because the kinetic energy is negative as per that given thing, because energy conservation, so that particle can't be found. Region B, yes, it can, all the other things we can find. Potential energy can be greater than the P can be negative. B depends on the height. Okay, the height can be negative height also. Above the pendulum released from the horizontal to the vertical hit the bobby of the same mass. Here are the same mass. Here both are having same mass, and there will be exchange in the velocity. The length of the pendulum is 1 meter. Calculate the height at which A will be raised after the collision. It will not rise because it is already said this velocity will get exchanged. Velocity exchange, velocity transfer because of the elastic collision, and this is same mass. 37. Ball here transfer the entire momentum to the ball on the table and does not rise at all. Okay, this formula I already showed you. A raindrop of this 1 gram falling from the height of the 1 kilometer hits the ground. Okay, we calculate the loss in potential energy, gain in kinetic energy. Is the kinetic energy equal to the loss of potential energy? No, it will not be equal because of the air resistance. We see loss of kinetic energy, loss of potential energy. The total energy mgh is the potential energy. Gain in kinetic energy will be this half mv square. Okay, now both are not same. Okay, because the part of the potential energy is used of in doing work against the viscous drag of the air resistance. Okay, because the loss of potential should be same as the kinetic energy, but in this case it is not because of this air resistance. Two pendulums with vertical box length is suspended such that one position is 10 degree. Okay, here we have to see the interval. Okay, which is the time period. Okay, so at this point t equal to 0, then here 1 by 4t, 1 by half t, again 3 4 4t is the one cycle here. 39. So here you see at okay, the pendulum, uh, when a t equal to 0, the potential energy of the pendulum B will have the total energy. The A potential energy A will be at the bottom, so 0. Kinetic energy of the A is also 0. Kinetic energy B also is 0. But at 1/4 of the that pendulum period, so it will B will come and hit the A. Okay, so the potential energy of B will become 0. Potential energy of the A also will become 0, but the kinetic energy of B, see, the B loses its potential energy and it gain the kinetic energy. Now this is half of the time interval, that is the left side up. Then potential energy B will be 0, but the potential energy gained by the A now. Kinetic energy of the A is 0, kinetic energy B of is 0. So the both A and B are transferring that energy. Okay. At this point again this much. Okay. Now you draw this for the A and B, they are totally opposite. Okay. Here t equal to 0, no collision. T equal to 1/4, the A and B colliding. Again 2/4 left side A, no collision. 3/4 again there is a collision. Okay, like this. So this period is important here, T/4, these things. Suppose the average mass of the raindrop and their average terminal velocity given, calculate the energy transfer. Okay, 40. Okay, mass, density they are given, velocity, area. Okay, this height. Okay, based on that they are computing. An engine attaches the wagon through the shock absorber of the length 1 meter. The system is total mass moving. Okay, here see, the 90% of the energy of the wagon is lost due to friction. The 90% lost means 10% is absorbed by the shock absorber. Okay. Okay, this kinetic energy, in that only 10% is stored in this spring. Okay, the 90% is lost after the due to that collision. 10% of the kinetic energy is this. Okay, okay, now this is the that spring constant. A adult weighing this much Newton raises the center of gravity 0.25 meter for each step. Okay, so there are 6 kilometer, that is 6,000 meter. Assuming that the body of the adult is capable of converting only 10% of the energy intake in the form of the food, calculate the energy requirement. Okay, there are 6,000 steps. This is for each step, and this much height is going. Okay, mgh. mg is this and h is this. Okay, this much energy, and only 10% of this is converted. So it is, so you have to the whole 100% is this. 10% of this is converted into the energy. And complete combustion of this petrol goes off. Test track or okay, including the mass of the Here the efficiency of the car engine is this much. So here 0.5 efficiency means 1 liter 1.5 into this much means that means which is used. We are given 3 actually. 3 this much is told because of the 0.5 efficiency we have to divide by 2. Okay, then after that this. A block of mass 1 kg is pushed up in the surface in the horizontal, okay, 30 degree, this is 30 degree, the force 10 per Newton force parallel to the incline, okay. Okay, these scenarios, the block is along the calculate the work done against the gravity, okay, can be 44. Okay, this block, this is the force due to mg sin theta. This is the force due to this gravity component on this line. Mg is the work done against the gravity. Mg sin theta in the distance. Mg sin theta in the distance. Sin theta is 0.5 and this is the work done. Against the friction, we have to calculate, consider that constant also. Friction, the frictional coefficient is 0.1. Okay, if you use that mg cos theta, cos 30 is 0.86, okay, this much thing. Increase in potential energy. Potential energy difference is mgh, okay. Height 5, how did he get? Because using this relation, this is 10, okay, 30, and the use that Pythagoras theorem, you will get the height of this height is 5. Okay, change in kinetic energy. Acceleration we found force divided by the mass in the acceleration, and the change in kinetic, from that we can find the velocity. So change in kinetic energy, okay, this much. This is based on that equation which I already showed, kinematic equation, okay. So here they given the for all the scenarios. A curved surface is shown here. The portion of this portion is the frictionless portion, okay, B, C, D. But here there may be friction. There are 3 spherical balls identical radii and masses. Balls are released from rest one by one. From here they are released, which is slightly higher than this C, okay. With the surface AB, ball 1 is large enough friction to cause the rolling sound without slipping. So ball A rolls due to the friction, proper friction, it rolls. Its rotation is proper without slipping. Ball 2 has a small friction. Ball 3 has a negligible friction. For which of the balls is the total mechanical energy is conserved? Okay, ball 1 and 3 negligible friction, so mechanical energy is conserved. But ball 1, there is a complete rotation, there is a rotation energy, so the energy is conserved here also. Ball 1 pure rolling without any friction, without any slipping, so the energy is conserved in this both 1 and 3. But for the ball 2, there is a friction, there is a energy loss. Which ball will reach D? So the ball 3 will reach, because ball 3 there is no friction at all, so it will reach 3. Balls which do not reach D, which of the balls can reach back A? None of them can reach back A, because the A rotation energy, it has to be opposite now, that is not possible, and the ball too loses some energy. Energy is ball 1 and 3. Ball 1 acquires rotation energy, ball 2 loses some energy, so they both can't reach C, but ball 3 can cross over. Ball 1 and 2 turn back before reaching C. Because of the loss of energy, ball 2 cannot reach back A. Ball 1 has a rotational motion. In a wrong sense, when it reaches B, it cannot roll back, okay, because of that opposite thing. A rotor accelerates straight up, ejecting air downwards, gas downwards, okay, in a small time delta t. It is a gas of mass delta m relative, okay, 46. Change in velocity of the rocket and the relative velocity of the gas downward, okay, this rocket and gas. Mass of the rocket capital M, mass small mass of the gas, okay. After that you will get this. Two identical steel masses on Young model 47, okay. We can go through this. A balloon filled with helium rises, okay, against the gravity, increasing potential. The speed of the balloon also increases. And how do you reconcile this with the law of conservation of the mechanical energy? You can neglect the viscosity for here. The density of helium is less than the density of the air, okay. 48, okay, shows, okay. So density of the volume of the balloon displaces volume of the air. So you can go through it. So as the balloon goes up, the equal volume of the air comes down, okay. It replaces the air. The increase in B and the kinetic energy of the balloon is at the cost of the VE of the air, because of the potential of the air which comes down, okay.